Okay, now we're good.
Okay, so any questions on 1 through 7? Logan?
6.
On 6? Okay, so when are you going to worry about this thing not making the loop? At the top or at the bottom?
Top.
Top, right? So here's the deal. Your total force at the top is going to be force centripetal minus Fg. So basically you subtract at the top and you add at the bottom. So, and this harkens back to question number 1 as well up there at the top. So if you're going to complete an inside loop, and this is going to be important, if you're going to complete an inside loop, okay? So like me taking this rubber stopper and swinging it around. If I'm not going fast enough, it doesn't complete that loop. So at a minimum, you want this force total to be greater than or equal to 0. Okay, so at a minimum it has to equal to 0 and you're going to be in a state of weightlessness. So you set this equal to 0, that's force centripetal minus Fg. You move this over, you get mg equals mv squared over r. Solve for velocity. You get v equals the square root of g, which is your minimum velocity to complete the loop. So up there at the top on problem number 1, it says, is it going fast enough to complete the loop? Okay? There's like 3 different ways that you can answer that question. One is if the total force at the top is a positive number or greater than 0, it'll complete the loop. If your force centripetal is greater than your gravitational pull, it'll complete the loop. Okay, that's another way that you can answer it. Or if you look at this, because this is mass times your centripetal acceleration minus mg. So if you want to get fancy, you can factor out a mass. So even if your centripetal acceleration is greater than 9.8 meters per second squared, you'll complete the loop. Okay, so there's a whole bunch of different ways that you can answer that second question on number 1. Is it going fast enough to complete the loop? You can calculate the minimum velocity if it's faster than that. If your total force is positive, if your centripetal force is bigger than your gravitational pull, if your centripetal acceleration is bigger than 9.8 meters per second squared, doesn't matter. Okay, but just pick one of those as your justification. Okay? Anything else? Vonda,
Number 7.
is that with the fighter pilot?
Yes.
Okay. So here's what's happening on number 7. So you're going into the bottom of this flight. So here's the fighter pilot that looks like a purple gremlin from a McDonald's Happy Meal, but stay with me here. So if the pilot is just flying along at level flight, just like you all were sitting here, right? If you're flying along just at level flight, how much force does your butt feel? Enough to overcome what?
Gravity.
Gravity, right? So if you're at level flight, the total force that you're going to feel is going to be force centripetal plus your normal force, and that normal force is just balancing out gravity. So right now, you all are feeling just the normal force. That's it. That's it. Remember, this is what you feel. The reason that you don't feel any centripetal force is because the room isn't rocking back and forth like this. Now, if I could take the room and make the room swing back and forth, what would you feel at the bottom? You'd feel heavier because you're going to have 2 things that that have to act upward. Your centripetal force, because when this gremlin hits the bottom of this curve, what does the gremlin want to do? Wants to go in a straight line. So I've got to have some centripetal force to make them change that direction. So at the bottom, I'm going to take whatever centripetal force there is to make them turn and add that to the normal force that you're going to feel because of gravity, right? So this is always present. The wild card is the amount of centripetal force. Now, the whole kicker is this is what you feel. What is your maximum thing that you can feel and not basically pass out?
90.
9 FGs. So over here, this is going to be 9 times FG equals force centripetal. Now, over here, your normal force, in this case, is balancing out your gravitational force. So we're going to put this as also as FG because your normal force is the same as FG, right? Because it's normal, it's a flat surface. So you've got a 9 FG over here and you've got an FG over here. So what can you do?
8G.
Yeah, you end up with 8 FG equals force centripetal. Substitute mg, substitute mv squared over r, boom, you're off to the races. So if all goes well, on number 7, you should get an answer of 10 to the, something times 10 to the 4th.
Is that something a really bad GPA?
Yeah.
Like really bad?
It's, that's a relative term.
Okay.
Okay, that's a relative.
What did Nick say?
Uh,
I was something stupid. Yeah.
Your answer to number 5, and this isn't huge-ish, should be something around your current age. That's a huge, for some of you, that's a big-ish. Your answer to number 3 should actually be a negative number.
Yes.
Okay, but don't flip out. All that means is that you're going over the top of a hill, but because you're going over the top of the hill, you have Mother Earth to keep you from falling inward. It just means that as you're going over the top, your body wants to keep going straight. That's why you're going to feel a bit light as you come up over the top of the hill, because your body wants to continue on in a straight line. Vonda?
Okay, so back on number 7. How can you find the centripetal force if you don't have the mass?
Vonda, how do you calculate FG?
Mass times gravity.
Mass times your gravitational acceleration. How are you going to find your centripetal force? mv squared over r. What's going to happen to your mass?
It will cancel out.
That's why I didn't give you the mass. This is why you work these problems with variables before you put in numbers. Now, if you're really hard up for crunching numbers, Vonda, make up a mass. Call it 10 kilograms, whatever. Because it's going to cancel out in the end anyway. But if you work it this way, it saves you that hassle of worrying about a number. So the reason I didn't give you the mass is because you don't need the mass. Okay? Yeah, masses will cancel out. Anything else on 1 through 7? Good, going once, going twice, sold, fantastic. Okay, now, let's talk about the whirling, hurling, spinning barrel of death, which is a bit overdramatic. So, I know this ride is up in Kansas City, where you walk in and you stand here and it starts to spin.
Yeah,
Okay? Anybody ridden that ride?
yeah, it makes me nauseous.
Okay.
World's Fun?
Yeah.
Yeah.
What do they call it?
There's like 2 of them.
Yeah, same idea. So if you're not familiar with the ride, you walk in and they get this barrel spinning really, really fast, and then they drop out the floor and you're stuck up against the wall. Okay? Now, let's look at this from a physics perspective, and then we'll talk about it from actually let's talk about it from a non-physics perspective. So if you're familiar with this, here's what's happening. Okay, so imagine this room is spinning really, 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 really fast. And I'm here like this, okay? Right? And now, McGriddle, you've ridden this ride?
Yeah.
So you're inside the ride, okay? There's the wall. How do you feel? Like, what do you experience?
Just like getting pushed. That's all you kind of feel like. I feel like you're almost going to go through the wall behind you.
Yeah. So you feel, and this is going to be important, you feel like you're being pushed against the wall, right? And you try and like raise your head, it's really tough to do, right? So you feel like you're being pushed up against the wall. So, and you talk to people and go, oh, I was pushed, right? So Now, if you think this through from a physics perspective, here's what would have to happen. Inside the barrel, there's this source of this force that you can't see. That's pushing out with this invisible force field that you can't see, that interacts with your body and pushes you against the wall. That seems reasonable. Sure. We have an invisible machine that emanates an invisible force that interacts with your body and pushes you against the barrel wall. No, it's horrible. What does your body want to do?
Fly.
Your body wants to turn into a projectile, right? Your body wants to turn into a projectile because your body wants to go in a straight line. So what's the barrel wall doing? What's the purpose of the barrel wall?
To keep you spinning.
Keep you spinning in a circle, right? Because let's say, for example, they could automatically remove the barrel wall. What's going to happen? Whoo! You're gone, sirs. Okay? You turn into a projectile at that point. So you feel like you're being pushed. So this is Newton's third law. So this thing is spinning, right? You're here like this. You're trying to move in a straight line. So what you feel is the action-reaction force based upon the barrel wall. So it's very similar to if Bree was sitting in this chair and I came from behind and I pushed Bree. So Bree's going to go like this, right? She's going to feel like she's being pushed back into the chair. But is there anything in front pushing Bree back into the chair? No, she just wants to remain at rest. She feels like that because of the action-reaction of her body against the chair. Okay? That's what she's feeling. But there's nothing in front pushing her. So when you're inside this ride, there is nothing inside of the ride pushing you against. You just want to move in a straight line. The barrel wall is preventing this. So you can simulate that on a small scale. So I'll take this rubber stopper, and I'm going to put it on the, here Max, give us a turn here. Okay? So I'm going to take the rubber stopper, and I'm going to put it on here, and I'm going to get this thing spinning. Okay? Oh, try that again. That didn't go well. Where'd it go? Oh, it's going fast enough. That's right. Underneath your, there you go. Try that again. There we go. Okay? Now, notice how it's staying up there, but if I slow down, what happens? Then it falls off. If I'm going fast enough, what does it do?
Stay.
It stays there. But if I slow down, it slides. Now, so let's look at the forces acting on that stopper once I was spinning it around, right? So here's, okay, I was holding on to this thing was going around, and here was the rubber stopper. So when this thing was spinning around, what forces were acting on the rubber stopper? There's three of them.
Gravity.
Gravity, which is going to be pulling it which way?
Down.
Straight down. Now, if that's the only force acting on that rubber stopper, what's that rubber stopper going to do?
Go down.
It's going to accelerate downward. Okay? But it wasn't, so what does that mean? There has to be an upward force acting against that gravitational force, right? Now, that's going to be friction with the platform, okay? So here's the deal. At a minimum, that frictional force has to equal the gravitational force. That's what's keeping it there. So I got friction acting up, I got gravity pulling down. So, and here's why this works. So like if you rub your hands together and your hands are just barely touching, there isn't much friction. But if you really push your hands together hard, then you generate a lot more friction. Same thing is happening here. Once I slow down, what happens to the, well, let's talk about the centripetal force. What's the direction of the centripetal force acting on the stopper? Inwards at right angles to the...
Velocity.
Okay, so as I slowed down, what happened to the value of that frictional force? It became lower. Because what happened to the centripetal force as I slowed down? It became lower because I was going slower, right? So when I was going really fast, that's like pushing your hands together really hard, okay? And that's generating a lot of friction. As I slowed down, imagine that you're pushing with your hands. They're still touching, but they're not touching with as much force. So you're not generating as much friction. So what happens is as I slow down, I generate less centripetal force, there's less friction, eventually gravity takes over, and it begins to slide down. So what that means is there's the minimum speed that I have to spin to make this thing go in a horizontal circle. So you go back to the definition of the coefficient of friction. mu equaling force friction over force normal. Basic idea. Now, in this situation, what does your frictional force have to balance out? Force of gravity, right? Because that's what has to keep this thing from sliding down. Now, remember, which direction does your normal force act relative to the surface? At
90 degrees.
90 degrees to it. So, if here's my surface, what's the force that's acting at a 90-degree angle to the surface? Your centripetal force is. So we'll put the centripetal force down here. So now I've got mu equals Fg over Fc. Now, in this case, this is going to be mg, and this is just going to be mass times my centripetal acceleration. So conveniently, Vonda, what's going to happen to the mass?
The masses will cancel out.
Masses will cancel out. Oh, okay, right. Okay, didn't get the mass, that's why. So here's the deal. So what I end up with is mu equals g over AC, right? So if you know the coefficient of friction, could you calculate the centripetal acceleration? What would you do? How would you get centripetal acceleration by itself? Yeah, multiply by AC and then divide back by mu. So your centripetal acceleration is going to equal g over mu. Okay? Now, notice that this isn't dependent upon radius, it isn't dependent upon mass. The only thing it's dependent upon is that coefficient of friction. Okay? That's it. Dependent upon the coefficient of friction. So, when you look at the information, let me see your paper. No, the yellow. Thank you. So, when you get to number 9, it says you're going to design this carnival ride and it's going to make a half revolution per second, assuming a minimum coefficient of friction is 0.15. Okay? So here's the deal. On that last problem, I've given you the coefficient of friction. Okay? You have this number, right? You know this number. You know what G is, and if you don't, God help you. Okay? So what you're trying to find is the centripetal acceleration. So you're going to go with this. Centripetal acceleration is g over mu. You have everything to find the centripetal acceleration. Now, here's what you have to watch. You're spinning at a half revolution per second. Is a half revolution per second frequency or period? That's frequency because it's an event per unit of time. Okay, it's a half a revolution per second. So how can you get period then? The inverse of frequency. Okay, they're inverses. So period is the inverse of frequency, or frequency is the inverse of period. Doesn't make any difference. Okay? So, what I would recommend, and some of you need to embrace this idea, that centripetal acceleration equals 4 pi squared r over t squared. You're going to find the centripetal acceleration from this, so you're going to know that number. You're going to find the period because you know it's a half revolution per second. So you can take the inverse of that and get the value of t. The only thing you're not going to know is your radius. So if all goes well in that last answer on number 9, you should get a radius somewhere between 5 and 8 meters. We're good. Anything else on that assignment? So here's what you want to think through. If mu gets bigger and bigger and bigger, in other words, if there's more and more friction, what's going to happen to your centripetal acceleration?
Look at smaller.
It's going to get smaller, so you wouldn't have to spin as fast to make that thing stick up there. So like, imagine that I've got like Velcro, you know, you want, if you really want to be safe, right? You'd have people wear like a Velcro suit and you'd have Velcro on the walls. You know, then basically you would have to spin it all. People would just stuck right there. So anyway. Okay, anything else? Once, twice, sold. If you get that done, get that, hand it in. If you need some more time, you can hand it in tomorrow. So, all right, Mad Max. Show us business perspective.
Did you like that, Max?
Yeah, that was good.
Did you like
You
that?
liked it that way.
You like that? So,
Yeah.
what's at the
Because I
core?
teach chemistry as a math class.
Well, I hate
Okay,
math.
it's core.
Why are you in this class then? This is nothing but a math class.
Every single
Why am
day.
I do too. Why I teach it. Okay. Anyway, all right. Huh?
I think I was like, why am I in this class? For this one, I'm too far in, so gotta finish it.
Yeah.
Yeah, I gotta go on Kansas Scholar.
Okay.
We're going.
We're going.
Oh, we're going.
Yeah, we're going.
As the
I was-
ladies parade in front.
Well, I was trying to get some good footage of you and Eli just arguing because it's always nice for them to have, you know, a little
a
break.
little background.
Yeah, well, yeah, and just like a little break in the notes.
comedic relief.
Because I mean, they miss a lot of the excitement. Yeah, they miss a lot of the comic relief from this class.
They
So,
hear
you
me
know,
talk a lot, so it's like, it'll help them.
It's kind of like
That's my
it's like the cartoons in Holy Grail. You need
Yeah.
a little break from the movie.
yeah, exactly.
Okay.
Gotta develop
All right. So here's the next big thing, and this is planetary motion, and you'll see why you study centripetal motion before you study planetary motion, because planets are moving in circles, and that's just basically centripetal motion. So that's why you study it first. But, so if you look at like the history of science, without doubt the oldest branch of science is, as far as a pure science goes, is astronomy, in terms of making observations and forming hypotheses and stuff like that. So, you know, they needed astronomy primarily for navigation, because if you've ever been out on the ocean away from land, you have nothing to look at except for the stars, and they would have to be able to use the stars to navigate. There was certainly like an agricultural aspect to it, okay? When do you plant, when do you harvest, you know, that type of thing. There's also a huge religious and mythological aspect to astronomy as well. So if you look at all of the cultures, Maoris in New Zealand, the Aborigines in Australia, Native Americans here, Africa, wherever, any place you had a culture, they always had a mythology associated with the stars because it was the great unknown. You know, we have our constellations, you know, like the Big Dipper, Orion, Sagittarius, whatever those constellations are. And the Greeks were great for that. The Greeks had, you know, all these different constellations and all the stories that were associated with them. And so this whole astronomy goes way, way back. It's more so than any other branch of science. It's intertwined into our story as humans. And so one of the big debates always was, what's the role and what's our place in the universe? And so for the longest time, everybody thought the Earth was the center of the universe and everything revolved around us. And it's kind of like...
You ruined the whole story.
It's kind of like this ultimate freshman mentality, that we are the center of the universe and everything revolves around us. Okay, it was. That was the story. And we felt good about it, you know. There was the biblical thing, you know, God made man in his likeness and put us on the earth. And it's like, oh, okay, hey, we're formed in the image of God and everything revolves around us. And we felt special, you know. It's like, wow, we're cool, right? And so, but not only was there that, there was also the observations. Now, it's going to be cloudy tonight, unfortunately, but today is actually a full moon. So to really understand what we're talking about today, you need to figure out where the Earth is and the observations that we make. So let's say here's the sun, and here's the Earth. and this is looking down on top of the North Pole. So here's the Earth, and we're looking down like this. So here's the first question that you need to answer, because if we don't have this right, all of our observations are going to be screwed up. So if you're looking down on top of the North Pole, does the Earth spin clockwise or counterclockwise? Which direction does the Earth spin?
Clockwise.
That's what Google.
Clockwise. I heard clockwise, and I've heard
It
counterclockwise.
don't.
Google
It
it.
don't
Okay.
spin. It don't.
It spins
We got a
counterclockwise.
50-50 shot.
It spins counterclockwise.
It don't spin.
Okay, so let's say
Been a flat surface spin.
that Matt,
What is
let's
wrong?
say that Matt with that nice loud T-shirt or sweater that he has
Sweater,
on
yeah.
is our sun. Okay, right?
Thanks.
So, give him a
Stand up and give us the. There you go.
Here we
okay,
go.
so that's our sun.
That's the sun.
That's my son
Okay.
right there.
Nope.
Okay. Now, so here's in Halloween. This is the only thing I'll associate with Halloween. So here's this gremlin or whatever it is, and Matt's the sun. Okay, and so here we are in Maze, America, right here. So here we are in Maze. There's the sun. What time of day is it? Noon. Why? That's directly overhead, right? So here we are at noon. Everybody cool with that? Now, if we're back over here on the opposite side, this is going to be what? Midnight. Because we're on the opposite side of Mount. Now, if the Earth spins clockwise, so I'm going to spin this thing clockwise. So here's the little gremlin, right? There's the sun. Midnight, we can't see Matt, right? But at some point, as if we spin clockwise, as we come around, at some point, we're going to be able to look and we're going to see Matt rise. Okay? So instead of sunrise, we're going to have a Matt rise. Okay? So, if the Earth spins clockwise, Bree, what am I looking at to see Matt?
Like what direction?
Yeah.
West.
I'd be looking towards California. Okay? So if the Earth spins clockwise,
Who wants
the
to look
sun
at
would rise
California?
in the west, and it would then, when we get over here, then it would set in the east.
Clockwise.
But if we spin counterclockwise, right? So here we are in Maze America. Then as we come around like this, now we're looking towards the east coast, and we're going to see Matt rise in the east. Okay? So, first idea is that the Earth spins counterclockwise, looking at it from the top of the North Pole. Okay? Cool with that. Now,
You should teach astronomy.
huh?
You should teach astronomy. I would take that class.
Is Matt? Huh? Is Matt the sun anymore? Like,
No, we're done
oh,
with that.
thank God.
Okay.
That hurt
So,
my back a lot.
now,
You didn't have to do that.
Yes, I did.
He's like, thank God.
okay.
It was hurting
now,
my back.
tonight is actually a full moon. All right? So let's talk about the moon very briefly.
Too bright.
So, here's the moon over here. This is an option. The moon could be here. The moon could be here. The moon could be here. Okay? So you have A, B, C, D. This is looking down on top. Okay? We have a full moon. Where is the moon on this A, B, C, or D when it's a full moon?
E.
Earth. It's at Earth. So how many vote A? Okay? What about C? B?
Yeah. I don't know. But everything's yes.
B?
Yeah.
Freshman
What
general
about B?
This is freshman general
I think it's E.
Now, let's talk about why couldn't it be C? There's two reasons it
We
couldn't
wouldn't
be
see
C.
it.
We'd be looking at a
Okay, number one, what are you looking at? Matt, now,
You have
this,
to move.
and Matt, you alone give this answer
it's at a
because of the
slight
shirt that
angle.
you wore yesterday.
Well,
What are you looking at if you're looking, if C is here?
Pink Floyd The Wall.
yeah.
One shot!
I listened to him and I knew that.
You
Actually have to
have
leave.
one
For
shot.
reference, for those of you watching on YouTube, he was wearing a Dark Side of the Moon t-shirt.
Matt, no, shh.
Oh, come on, that's funny.
No,
This is funny.
no. You have one shot. Never calling on you. That's going, all right, cool. Okay. So, number one, you're looking at the dark side of the moon. What's the other problem? Well, beyond that, what else are you looking at?
The sun.
The sun. Okay? Small detail. Now, what about over here? Does A seem logical? Yes, because the dark side of the moon is facing away from us, and you're seeing the lit side. Okay? So when you have a full moon, this is where it's located. What do you call it when the moon's over here?
Eclipse.
New moon.
A new moon. Okay, this is when you can get a solar eclipse. Okay? We'll talk about that later. Now, here's the question. And we'll see if you all have made any observations about nature in your 18 or 17 or 18 years on this earth. When it's a full moon, listen to me very carefully. What time of day does a full moon rise? Like if I said, hey, we're at a full moon. We're going to meet together as a class and we're going to watch the moon rise. What time of day should we gather? I'll give you four choices. I'll give you four choices. We could gather at noon when we're here, okay? And again, this is looking down, so here's the dark side of the earth. We could gather at noon. This would be sunset, midnight, sunrise. So this is the $1 million question. If you want to watch a full moon rise, what time of day on earth is a full moon going to rise?
Sunset.
Vonda, if the sun rises, how is it a trick question that the moon would rise?
I can see the moon during the day though.
No, we'll get into that, Vonda. We'll get into that. Okay? This is just a full moon. Now look. At noon, can you even see a full moon? When it's noon and it's a full moon. Because the moon is over here, right? At noon over here, you can't see it because the earth is in the way. Right?
Yeah.
Yeah.
Huh? What, Felix?
He said
So
midnight.
you know, like the werewolves, they have the moon, like when it's at midnight, right? Swear to God, dude.
So many Twilight birds.
Now,
In the spirit, I swear to God.
at midnight, you're here. Where's the moon going to be?
Directly overhead.
Directly overhead. Right?
That's not rising.
Right? Now, which direction does the Earth rotate on its axis? Counterclockwise. So, as you come around like this, at this point in time right here, this is when you're going to be able to see, this is when you're first going to be able to see the moon. But, what's going to be happening relative to the sun? Is the sun going to be rising or is the sun going to be setting? The sun's going to be setting. So a full moon will rise when the sun sets. Okay? Now, if it wasn't going to be raining tonight, you could go out and you could see the full moon rise. Literally, you could stand here and you could see the sun set on the west, and you would see the full moon rise on the east. Now, tomorrow morning, when the sun comes up, what are you going to see? You're going to see the moon set, and you're going to see the sunrise. Okay? Now, let's go back to what Vonda said. Vonda is right. Sometimes you can see the moon during the day. So let's say that the moon is right here, okay? And we'll call first quarter. The moon is here. Here's what I want you to look at. At sunset, okay, if the moon is here at sunset, where's the moon going to be? Directly overhead. So if the moon is here, you would see the moon rise at noon, and then as the sun sets, it would be directly overhead. So this is why sometimes you can see the moon in the afternoon, okay? But you won't see a full moon. You're only going to see a partial moon. Now, the same thing is going to be true over here. If the moon is over here, you can see it during the day because you're going to be in sunlight and it's going to be above that horizon. So this is why you can sometimes see the moon during the day. But the moon has to be over here or it has to be over here in its orbit. Okay? Go with this.
Yeah.
Now,
One
Olivia,
question. How do you know where the moon, like, where the moon is compared to the Earth on its rotation?
what in terms of what?
In terms of
Like the moon calendar.
yeah, I don't, well, in terms of like how you know where it would be to see it, like what time of day to see it.
Well, basically, the beauty of this is that the moon basically operates on a 28-day schedule. So roughly, we're going to have a full moon like on the 24th of October. So November 24th is when you're going to have your next full moon. So if you kind of get an idea of when you have a full moon, then you can kind of space that out and go, okay, hey, the next full moon is roughly going to be about a month later. So, but it's cool, if you ever get the time, it's cool to track the moon and see where it's at. Personally, my favorite time to see the moon is when the moon is just about here in its orbit, because what you'll see is you'll see it just above the western horizon, or just before, what you see is the sunset, and you'll see just a little sliver of the moon. That's my favorite phase of the moon.
So you like the toenail phase?
Yes, yeah, exactly. You're just seeing this tiny sliver of the moon right after the sun sets.
That's my
Okay.
favorite phase too.
Now,
Won't be
what are the
embarrassed.
two interior planets?
Venus and Mercury.
Venus and Mercury. So here's the deal. Is it possible to see a full, is it possible at night to see a full Venus or Mercury like you see a full moon?
No.
No.
Because at night we're faced away
Well, first off, where are they going to be?
closer to
They're
the sun.
interior planets, right?
Yeah.
So let's talk about, let's say Venus is here. If Venus is here, could you see a full Venus?
No.
No, because number one, you're staring at the dark side of it,
Yeah.
and you're staring at the sun. Small problem. Now, what if Venus is over here?
You can't see it.
Then you've got the dark side.
Time to look
No.
at it.
No, sorry. No. So, you're staring at the dark side, right? But what's the problem?
The sun's on them.
Yeah, the sun's in the way.
Okay.
But what if it's over here? Then could you see it?
You can see a partial Venus.
Yeah, but you can only see partials of them. So this is why Mercury and Venus are known as the morning and evening planets. Okay? Because you can only see them, if here's the Earth, you can only see them here, and this would be towards sunrise, or you could see them here, and that would be around sunset. So you can never see a full Mercury Venus. Could you ever see Mercury or Venus at midnight?
No.
No.
No. Why?
Because they're on the opposite side of Earth.
Yes, you're over here.
Yeah.
Okay? Now, this could backfire, but I'm just saying this is an option if you're out on a date. It's midnight. You're out on a date. You're trying to get a feel for how bright your date might be.
Ooh.
I'm just saying. Just stay with me here. So, now this is where this could backfire. So you can pick like a random star and point to it directly overhead at midnight and go, oh, look, there's Venus. Now, if your date doesn't know anything about astronomy, they'll go, oh, yeah, I see it. That's pretty. That's Venus. Okay? And at that point, you go, you have no idea about the relative positions of the planets. Now, this is where it can backfire, though. If your date goes, you're an idiot. Okay? There's no way that's Venus. okay? Because of the fact that Venus is an interior planet. So that can go both ways. Either way, probably a deal breaker, okay? So I don't recommend it. But I'm just saying, it's like, Mr. Dave's gonna go, you're an idiot, okay? There's no way that's Venus. Okay. Now, what's our closest exterior planet to the Earth?
Mars.
Mars. Now, is it possible to see a full Mars?
Yeah.
Yes. Okay, just like you can see a full moon. Because if Mars is over here, this is what's called being in opposition. If Mars is over here, here's the Earth, you can look and see, you can see a full Mars just like you see a full moon. Saturn, Jupiter, all the exterior planets, you can see a full view of those planets because they're on the outside. Okay, so we've got this established. So one of the big debates is what type of system that we live in. So one of those was this geocentric, and we think we're the bomb and everything orbits around us. So here's where this goes south in terms of observations. If it's a full moon, you're going to see the moon rise in the east. You're going to track it. You're going to see it set in the west. And you're going to see this moon go across our sky, and it's going to go across like this, and it's going to set. Everybody cool with that idea, right? That's what you're going to see. Now, if I said, okay, class, tomorrow, here's the deal. We're going to meet out in the parking lot. We're going to watch the sun the entire day. We're going to track the position of the sun. Okay, we're going to be out there in the parking lot. We're going to have some breakfast burritos, and we're going to see this big, bright star appear over the eastern horizon. At noon, we'll fire at the grill, have some burgers. Okay, it's directly overhead. Sun sets, we're going to fire at the grill again, maybe throw some steak, some shrimp, something like that. Okay, right? We're being good. We're being good, right?
Can we actually do
Now,
this?
but here's the deal.
doesn't
You're
sound so
going to
bad,
see
though.
the sun take the exact same path as the moon did. You're going to see it rise in the east, you're going to see it track across, and you're going to see it set in the west. So, the moon does that, and you say, oh, the moon's orbiting us. You see the sun take the exact same path, and you go, oh, no, we're orbiting the sun. Now, this is why this took a leap of faith. Because to agree that the sun is stationary and we're the one that's spinning implies that right now we're traveling at about 400 and some odd meters per second, which is faster than the speed of sound. And we're on a rock that's spinning. Okay? So if you've ever built like on the total world, right? Okay, you might be going maybe 17, 18 meters per second, and you're like going, whoa, okay? And now we're on a rock that's going over 400 meters per second. Yeah, we're just standing out. We're just showing up. Okay, not a big deal. We don't get the feeling that we're moving at all. But here's the analogy. Here's a similar type story. If I go over here, and I start on this side, and I'm going to walk, and I'm going to end up over here. And I'm going to say, what happened? What are you all going to say? I started over there, and I ended up over here. That's what you all are going to say, right?
Yeah.
Because you all get the idea that you're stationary and I'm moving. So that's what happens with the moon. Hey, boom, we take this path. Now, I would say you all are wrong. I'm stationary, you all moved around me. Okay? But that's the flip of the story that you got to take. If you subscribe to a stationary sun and a spinning rock, be like, I never moved, you all moved around me. But that's the flip that you had to make in terms of the observations. So, one of the first big hitters on the story is a guy by the name of Nicholas Copernicus. He was a Polish monk, which means he worked for the churches in the 1500s. So here's the first one that really came up with a working scientific paper that said that we live in a heliocentric solar system, meaning a sun-centered. Now, he didn't want to get in trouble with the church, so he says, look, publish this paper after I've died. Okay? So he dies, the paper gets published. Hey, we get some ideas, and the stirrings in the scientific community goes, maybe we got to give this idea of a sun-centered solar system some thought. So that was kind of the first big idea in terms of a heliocentric solar system. So the next two big hitters, their story gets intertwined. A guy by the name of Tycho Brahe. Okay? If you ever get bored, Google Tycho Brahe. It's Tycho Brahe. So Tycho Brahe was a Danish nobleman, which means that he didn't have a job. True story. So Tycho Brahe is known for three things. One is a great handlebar mustache that typically comes down to about here. More like a Fu Manchu kind of look. He also had a gold nose, so he was the first one to have bling. Legend has it that he was in a sword fight with another nobleman about how to solve a math equation. They took their math really serious. And swords were drawn, and they got into a sword fight over how to solve this equation, and he got his nose cut off, and he had a lot of money, and he didn't want to be seen without a nose, so he had a gold nose made, and that's what he had. I don't know how he held it on, and I don't know if he could smell. Don't ask me, I don't know.
could smell
Those
it.
are always the two questions
could
that are
smell.
asked. I don't know.
He could.
I
Okay,
got a hit real nice. Just put
He
gold.
could smell a lot of gold, but he could
Okay, I don't-
his smell worked.
now,
It did work.
but here's what he did. So Tycho Brahe, this is before the telescope. So Tycho Brahe basically had his own island in the North Sea. And he built this grand observatory out there. This is before the age of telescopes. And he spent like 26 years compiling all of this fantastic data about the motions of the planets. Planet actually comes from the Greek word meaning wanderers. So the planets, Mercury, Venus, Mars, Earth, whatever, they move relative to the fixed constellations in the sky. So that's what what the word planet comes from. So he had all of this data. He didn't really know what to do with it. He actually came up with his own model of the solar system called the Tychonic solar system, and it was kind of a blend of a heliocentric and geocentric system. But the point is, he had like volumes of data, and it was the best data that existed in the world. So, next comes Johannes Kepler. Johannes Kepler was a mathematician, but in his mind, he was on a mission from God. And his mission was to figure out a mathematical relationship to describe the motions of the planets. Now, unfortunately, Kepler knew he was not going to live long enough to come up with all of the data and come up with a mathematical relationship. But he heard about Tycho. So Kepler goes to Tycho and he says, yo, I'm on a mission from God. I need your data. Because I felt that this is my job, is to come up with a law, a mathematical relationship to describe the motions of the planets. Tycho says, hey, I like you. So, and Tycho says, so that I have not died in vain, you can have the data when I am no longer in this earth. So Kepler's going, cool, I'm on a mission from God, I'm going to get his data. Tycho dies, but his family says, no, we really want to hold on to it, we're not going to let you have it. So Kepler at this point is faced with a moral dilemma. He goes, I'm on a mission from God to develop the laws of the universe. I can't get the data because the family has it. What's a guy to do? So there's various versions of the story, but this is my favorite one. So Tycho breaks into the castle. Kepler breaks into Tycho's castle, steals the data, and escapes back to Germany where he starts doing all his calculations. So the first three great laws of planetary motion were developed by stolen data from Tycho Brahe, who had a gold nose and a handlebar mustache. You can't make this up. Okay, so Kepler starts crunching his numbers, and this is what you've got either on the single sheet or on the front page of the lecture notes that you have. So I'm not going to expect you to know all three laws, but in terms of like exactly what they are, just the broad idea. The first law is the law of ellipses. Now, this created a controversy because the planets were the realms of the gods. They viewed the circle as the perfect geometric shape. This is why wedding rings are circular, because it's like our love has no beginning, it has no end, whatever. Okay? And people wonder why I'm single. So, basically, when Kepler says, hey, it moves in ellipse, and by the way, an ellipse has two foci, in case you were wondering. So, what do you call an ellipse that only has one foci? A circle, right? So the farther apart these foci are, the more elliptical it is. So this created a bit of a controversy because you're going, whoa, God tried for a circle, he messed up, and we ended up with an ellipse. Ew. I'm just telling you, people didn't like this idea. So all you have to know, planets move in ellipses. That's all you have to worry about. Second law is what's called the law of equal areas and equal times. So what that means is this. The sun is one foci. If I could erase that, though. So what Kepler realized that if you took any period of time, let's say it's 10 days, 30 days, it doesn't make any difference. Let's say we take 10 days. So if you drew a vector from the sun out to the edge of the orbit, and then another vector out to the edge of the orbit 10 days later, you can find the area swept out during that time. Okay, it's going to be a certain geometric area. Now, if you came in here when it's closer, and you also did a 10-day sweep, this area here is the same as this area here. Okay, so that's why it's called law of equal areas and equal times. Now, the only way that can happen is if you have a bigger arc length. You have a shorter radius, so you have to have a bigger arc length. Out here, you have a bigger radius, so you have a smaller arc length. So here's all you need to know about the second law, is that when it's farthest away, when you have a bigger radius, that means that you're moving slower. Okay? That's all you need to know. And then, when you have a smaller radius, you're moving faster. So what that means is that you're always changing speed. You're slower, further away, you're faster when you're closer. So it's like you're going out, slowing down, okay? And then you speed up when you come back around the sun. So you have your greatest velocity when you're closest. That's all you really need to know about the second law. Now, the third law. Third law, and this is what's on your equation sheet. Period of A squared, period of B squared, was radius of A cubed, radius of B cubed. So what this does, this allows you to compare the period and radius of two objects, now listen to me, that orbit the same center, okay? They have to orbit the same center. So like we can compare Earth and Mars because they both orbit the sun. But we could not compare Earth to a moon of Jupiter because the moon of Jupiter is orbiting Jupiter and the Earth is orbiting the sun. So this works, it's a beautiful ratio, but they have to orbit the same center. And later on you'll see why that works. Now, this is the only time I will ever tell you this in this class. Since these are just ratios, it doesn't make any difference what units these are in. It does not matter, just as long as they're in the same units. So this could be years and years, it could be days and days, it could be hours and hours. Doesn't make any difference, as long as they're the same. These could be kilometers, light years, meters, inches. It doesn't matter, because it's all a ratio. This is the only time I will ever tell you this in this class, is that it doesn't make any difference what units that they're in, as long as they're the same. Now, here's the other thing about Kepler. He said, okay, here's the sun, here's the Earth, for example, here's Mars, okay? Now, Kepler didn't know the distances from the Earth to the sun. He did not know this distance. And he's trying to do all of this late 1500s. No calculators, no Google, no Siri, didn't even have Oreos. Okay, it was a horrible existence. So, if you're trying to find this mathematical relationship, what numeric value do you want to use as often as you possibly can?
1.
1. Okay, that's what you're going to try and use. So what Kepler did, he says, hey, look, I don't know the distance from the sun to the Earth. He didn't know the actual distances. So he said, I'm going to let that be 1 astronomical unit. He says, I'm just going to make this simple. I don't know the distance. I'm going to let this be 1. So therefore, Mars has to have an orbital radius that's bigger than 1 because it's further out. Okay? Simple. Now, if you're Kepler, what are you going to let the period of the Earth be? 365 days or 1 year?
1 year.
1 year. Okay? Because that's easier to work with than 365 because you're doing all of this by hand. So, here's the shortcut. Let's say that we check CNN, news flash, NASA discovers new planet. This new planet X has an orbital period of 9 years. Okay? And we want to figure out the orbital radius of this planet. We know it takes 9 years to go around. So, here's what you're going to do. Personally, what I would do is I would cross multiply. So this is going to be Earth, planet X, Earth, planet X. Okay? That's what we got. So it doesn't make any difference which one you put on top as long as it's the same. So you got period of the Earth squared, radius of x cubed equals period of x squared, radius of Earth cubed. Now here's the beauty. What's the period of the Earth? 1 year. What's 1 squared?
1.
1. So that just becomes 1. What's the radius of the Earth? 1 astronomical unit. 1 astronomical unit cubed is 1. So basically, this boils down to that period, 9 years squared equals the radius of x cubed. So how are you going to find the radius of x? You're going to square 9 and then do what?
Cube root.
Then take the cube root of it. So,
So you can get 3.
if you can let 2 of the 4 variables have values of 1, then it just boils down to the radius cubed is proportional to the period squared. Okay, that's the shortcut. Okay, let me see. Bree, do us a favor. Give everybody one of those.
Are you kidding me? There's like 30 seconds left.
No, I'm Matt.
You're okay, Matt. Matt, come
Come
on,
on,
Matt.
Matt.
Matt,
Stop
come back.
it.
Stop it. Matt, come back. Matt, Matt.
I'm sorry. I'm running away, Matt.
Matt, I'm
Wait,
sorry.
Okay,
Unless I
should
gotta
be-
make it.
You have anything? Yep.
Can
Can I give myself one, Chad? Give myself one.
What?
Oh, Max, we also got a purple paper.
Kidding me, Eli?
You get one?
Eli,
Really appreciate it.
Now, let me explain what you need to do for tomorrow.
Dang, bro, he's hungry.
I said Eli, you just said, ah.
Said Eli, eat this. I said, I ate it.
Nick, stop trying to take all my papers.
Okay, so here's what you need for tomorrow. Purple sheet, there's only one side, it's all calculus law
I
stuff.
didn't get that one.
Which one?
That one.
Sorry. Did you go on break?
I got one.
Okay, now, here's the other thing that you need to do. You need to go to this graph. So it's a polar graph, laid off in degrees. So what you're going to do is you're going to go to like October 1st. October 1st, Mercury is at 114 degrees and a radius of 0.319. So what you're going to do is you're going to come over here, you're going to find 114 degrees, which is over here kind of in the second quadrant, and you're going to find 0.319 and go around like this, and you're going to plot that point. Here's what I would recommend so you don't go stir crazy. Most of these radii are between 0.3 and 0.4. I would take a pencil and shade in that 0.3 line and shade in that 0.4 line in a different color, or somehow differentiate them. It's just going to make life simpler to plot these points, okay? So you want to plot these points. It's going to make a circle. Actually, it's going to make an ellipse, okay? Because Mercury travels in an elliptical orbit. So then, about every third point, write down the date, because eventually tomorrow we have to know where Mercury is at certain times. So plot every point, but about every third point, write down the date. So like on that first one is October 1st, so you could just put like 10/1. You don't have to put the year with it, it's 1990. It's going to be the same date repeating again and again. So about every third point, put the date and plot every point. So you got the purple sheet, plot the points, and that's what you got for tomorrow. If you haven't handed in that purple sheet or that yellow sheet from yesterday, you can hand that in tomorrow. If you've got it done, get that handed in.